Okay, the next talk is by Jordi Pons. Jordi Pons is doing the PhD here at the UPF, at the MTG. In fact, he was one of the first people at the MTG completely crazy about deep learning, and he succeeded in converting most of the MTG into deep learning. So I don't know if that's good or bad, but that's the reality. And so at the beginning, he was mainly working trying to figure out architecture, since most of the models that we have been using come from other fields, especially image. So the idea is, okay, how can we adapt those models and develop specific architectures for music? But the talk today is not on that, it's on something else. Yeah. So all yours, Jordi.
Yeah, it's about classifying environmental sounds, and this work was done last summer here in Telefonica Research, so here in Barcelona, and I was supervised by Joan Serran, who's actually here. So actually, the kind of the direction we take here is kind of very different from kind of what people has been trying to address now. So it has to do with the data, right? So here we said like, well, we need more data. Let's try to do active learning to get more data. Or I don't know, let's try to do data augmentation with synthesized data. Well, here, kind of what we try to do is to, well, what happens if we have just very few training instances for building deep learning audio classifiers? And this is exactly the scope of our talk. So, well, the first question is actually, well, so how can we do that? And, well, the first kind of naive answer to this question is, well, let's try to just use the standard deep learning pipeline, and let's just regularize strongly the solution space. And hopefully, here we'll have some chances to generalize. But, as we'll see, actually, the deep learning pipeline, the standard deep learning pipeline here will fail. I mean, this is not a kind of a new idea. Actually, this is something that we'd actually expect. So the question is, can we do better? And to this end, we'll propose actually to use prototypical networks. And actually, we are the first ones to propose to use prototypical networks for the case of audio. This was originally proposed in the context of image classification for future learning. And basically, kind of conceptually, the idea behind that is that we have a nearest neighbor, but is learned end-to-end. Instead of having some kind of feature space that is defined by several features, here the features are learned with a neural network. So this is one idea we propose here, but of course, if we have just very few training instances, maybe we want to try to leverage external sources of data. And this is exactly what we propose to do here with transfer learning. So let's start, and I want to first briefly talk about the methodology I will follow in this presentation. Basically first, let's discuss which are the two data sets I'll be considering for this work. And here, this is, as Xavier said before, is not about music. In this case, it's about environmental sounds. So the first task is about classifying which sounds are in the audio. So it's event recognition, and here, for example, we want to identify if there's a car or if there's a dog barking or stuff like that. However, in the second data set, the goal is not to classify which things are there, but kind of classify the context, the acoustic context where we are. And here, for example, we want to classify if this audio was recorded in a park, in a home, or an office, and so on. Okay, so these are kind of the two data sets we'll be considering here. And then I will be presenting the results in graphics like that. And here the idea is that we have the two data sets that I have just presented, the acoustic scene classification and the acoustic event recognition. And as I said before, we want to study how these different deep learning models perform when we have very few training instances. And here, the idea is that we will be sampling from the data just one training example per class, two training examples per class, 5 training examples per class, and so on. Okay, so as we see here, we have more data, and our models that we have represented in these lines here improve when we have more training data. Basically, we see that here the accuracy, the higher the better, keeps improving when we have more data. Then, what are these other lines that we see there? Well, basically, we have in black below is the lower bound that we have, and basically it's a random classification. So it means kind of we just randomly select a class, and we'll get this accuracy. Now, what are the two other lines up there? Well, they define kind of the upper bound. So these are state-of-the-art results out there in the literature of people who actually trained some fancy deep learning models with all the training set. Okay, so this is kind of the best chances we have to, I mean, kind of the best result we can get. So the lower bounds in black, the upper bounds in these fancy colors. And now our goal is to place our different models that we'll be proposing and studying throughout this kind of graphic, like this one that we have here in gray, that is MFCC's plus nearest neighbor, a very simple baseline to get the reference. And we'll be placing the models here in order to see which one kind of get higher. Okay, this is what we'll be doing now. So let's first start the first idea kind of we want to try, which is to show how actually the standard deep learning pipeline would work under this context where we have very few training instances. So first let me introduce you, which is the input I'll be considering. So basically we use log mail spectrograms as input, and we'll be considering 3 models. Yeah. So here now the goal is to try to regularize these models. So kind of the main form of regularization we study here is trying to minimize the number of the parameters. So first of all, we start with SBCNN. And this one actually is a state-of-the-art in several data sets and is inspired by AlexNet computer vision architecture, so kind of the first wave of deep learning models, but still for these tasks work very well. Then our goal was to try to make this number of parameters smaller, and basically we make it 5 times smaller. So you see, and then we have the BGG. Basically what happened here is that we removed this dense layer, and we basically have a more kind of fully convolutional pipeline, so this means less parameters. Still, this model pretty much inspired with computer vision architectures. And then we want to reduce even more, and here we make use of domain knowledge for trying to make this model even smaller, and here we just consider a single layer CNN with vertical filters that can capture these timbral traces that might be present in the spectrum. So by means of using domain knowledge, we can make now these models even smaller, okay? And now we want to see how these perform, and to this end, we'll be placing these models into this graphic that I have presented before. So let's see how they work. And here we have those. Interestingly, we see that, well, interestingly, no, it's actually what we expect, right? It's nothing new that these deep learning models would actually fail when we have very small training set. So basically, especially we see these for the acoustic scene classification, and for the acoustic event recognition dataset, we see that, yeah, maybe the timber one gets slightly better results, but overall they have kind of a hard time trying to improve this very silly baseline that we consider here. Now, so we have seen that deep learning actually fails at the task of learning from very few training instances. The question is, can we do better? And here we have one of our answers, that is protypical networks. So since this is kind of a new concept for the audio domain, let me briefly introduce you what protypical networks are. So basically the kind of core concept here with protypical networks has to do with computing a prototype per class. So these prototypes are basically representatives of the class that would kind of define something like that. So basically in orange you see 5 training points that are data that are projected in a latent space. In this latent space, then we want to compute the prototype that are these dots in black. So basically, these dots in black, as you can see, are the average of all these embeddings in this latent space. Yeah, so basically, we project our training data in the latent, and then we have an average per class of all these points that are represented in the latent space. And it's actually what we see this in this function, and kind of the way we compute these prototypes is just the mean. Okay, so remember that previously I mentioned that this was kind of a nearest neighbor model trained end-to-end. So how do we learn this embedding space? Well, this is actually the next step of the model, right? Once we have defined conceptually the model, now we need to learn this feature space that is defined by this embedding. That in this case is in the function there is f, this function that we want to learn, and is parameterized by a BGG model here. So now the goal is to learn this kind of feature space, this embedding space, so that the classes, these prototypes, are separated, and then we can classify those properly. And then the question is, how we classify within this context? Well, so remember, again, I said this is a nearest neighbor learned end-to-end. So basically, we pick the prototype that is closer to our query data. So basically, we take our X, that is our audio that we want to classify, we project it into the embedding space, that would be this white point there, and then we do the Euclidean distance with respect to all the prototypes, and the one that is closer, this is our class. That's here kind of the intuition of why this is kind of a nearest neighbor learned in the end-to-end fashion because the features come from this BGG that is learned. Okay? Well, don't worry about the details, of course. You can go to the paper and carefully check that, but conceptually, this is the idea. We kind of project the data into an embedding space, we take the one that is closer. Okay, so now we know what prototypical networks are, so let's see how this works. So remember, these are our results. Now let's place the prototypical networks results on top of this in order to see how it works. And actually, we see the prototypical networks overall improve our results. And it's important to note, although, I mean, this graphic is kind of very compact, but the margin of improvement in most of the cases is pretty much consistent around 10%. So kind of learning from very small training data, we kind of gain 10% by means of running this kind of neural networks architecture. So this is the results of prototypical networks, but still we see that when we have very few training instances, the results are not kind of very good, right? We are 20% and like that. Can we do better? Well, the answer is yes, we can do better by means of using transfer learning. So let's briefly introduce what transfer learning is so that we are on the same page. So basically, the goal of transfer learning is to leverage external sources of data in order to be able to pre-train a model and then fine-tune our models with the few kind of training labels we have in our target task. So this is exactly what we'll be doing. We'll be considering a very big data set of acoustic event recognition, 2 million YouTube audios. And then once we have pre-trained this model with this, then we'll be kind of learning the last layer of a classifier for fine-tuning for each of the tasks there. So basically, we'll be using a BGG-like model for the pre-training, and then we'll be putting just one layer for the kind of the output of the classifier to fine-tune for each of the data sets. Okay, so this is kind of the canonical form of transfer learning. Let's see how it works. And there we go. We place our curve here on top of our best result that was prototypical networks, and we see that it consistently kind of improved the results, especially in the cases where we have very small training data. And actually, I think this result is particularly remarkable because with just one training instance, we can get almost 40% accuracy in both cases. Okay? So let me go to the last slide, to the conclusions. So we wanted to train deep learning models for building audio classifiers with just very few training instances. We were curious to see what can we do there. Actually, kind of the main discourse there is, well, use lots of data. Well, what if we don't have lots of data? Can we do something? And the answer is yes, we can do something, but not by means of using the standard deep learning pipeline. Actually, we have seen that this dramatically fails at the task. But if we don't have lots of training, lots of kind of additional data to leverage, as we did with transfer learning, maybe a good way to go would be with prototypical networks. But if we can leverage an external source of data like we did with transfer learning, maybe this is the right technique, because with just one example, we could get this 40% accuracy. You have code available to reproduce kind of these results, and if you want more information, you can read our paper where you'll find out how we computed all these results without even a validation set. So thank you very much.
Okay, any question?
Hi, very nice work. I didn't get well, when you use the transfer learning, you are using the prototypical network approach too?
No, here no, but in the paper we do it. I just didn't want to kind of put too many things into the presentation. But actually when we combine, so here we don't. Here we just use the kind of canonical form of transfer learning. It's just kind of fine-tuning the last layer. But if you combine transfer learning with prototypical networks, it doesn't improve. That's why I just put this result. Kind of the canonical or traditional form of doing transfer learning works better in this case.
Okay,
this is what we found, yeah.
Just a question about this transfer learning. So if I got it correctly, the task that you trained on was also acoustic event recognition, right? So in what sense is this transfer learning? Because for the other one, I mean, I see it for the other one, for acoustics in classification, but there actually the results get worse very soon. Thank you.
Yeah, that's. I mean, again, I just had 10 minutes, so I could not discuss all this. Again, I just had 10 minutes, so I could not discuss all this. You have all these discussions are included in the paper and much more. But yeah, you are right. So here, the source and the target tasks are the same for the urban sound 8K dataset, but are different for the acoustic for the audio set and the acoustic scene. So that's exactly the reason why we choose these two, because we wanted to see if out of domain what would happen. And actually we see that when we have very small training instances, like 1, 2, 3, it still works. But when we have more data, then prototypical networks kind of win. And this is particularly interesting because a model that was trained from scratch with much less training data was able to overcome the one that was pre-trained with another task with 2 million training examples. So actually, this model there, when it has 100, it has seen 2 million examples before, but still prototypical networks outperforms it. And I think this result is pretty interesting, actually. Yeah, so I completely agree with what you said. And in the paper, we all do this discussion as well, yeah.
Okay, so let's thank Jordi again.